All right, guys, I know this is the inversion of the usual professor-student relationship, but since I've been promising your homework for a long time, and it's your next problem set for a long time, and it's still not done, I can just say the dog ate my homework. I promise you'll have it next Tuesday. I'm trying to come up with decent problems, and what I've come up with was a linear combination of too easy and impossible. So when you get it, it'll be worth the wait, I hope. Sorry about that. Okay. I'm going to invert a little bit the order of presenting some of the material in a way that I think will make life a little easier. So actually today we'll talk about the amplituhedron. Because we can before getting there, let me just summarize the story of the last number of lectures, last 3 or 4 lectures. We started with there's a physical idea, which is to eliminate virtual particles. And only talk about on-shell processes. Associated with these on-shell diagrams gluing together the basic black and white vertices, the basic 3 particle amplitudes. And then you can explore this for a long time. You can explore it in a variety of ways. You discover that just the act of gluing them together, or even better yet, the act of nicely representing what these 3 particle amplitudes are, involves a little integral over a G13, G23 in this case, and a little integral over a G13, and that these pictures are actually associated with some structure, some part of GKN. And you can do all of that just from the motivation of thinking about on-shell diagrams. You can discover that there's reduction. That means that even very complicated on-shell diagrams are secretly very simple, just pulling out a bunch of d-logs from all the bubbles that you get. So you might naively have thought that on-shell diagrams are just as complicated as Feynman diagrams, but there's a finite number of them, right? There's a finite number of different ones. Furthermore, they're not unique. They're relations, which come from merge, unmerge, and much more importantly, the square move. Okay, so this kind of starts turning in this physical question of looking at what you get by gluing together on-shell diagrams gradually into a sort of a mathematical problem of just trying to understand graphically what reduced diagrams are, what set of diagrams can be turned into other ones under these merge-unmerge moves. And slowly by slowly emerges that the invariant content of these pictures is actually associated with a permutation, right? That's quite surprising, right? We start with on-shell processes and we end by realizing that the invariant content is given by this permutation. And all of this is a kind of a process that you might imagine going down if you just cared about gluing together 3 particle amplitudes. Oh, of course, sorry. The other important thing is that these are not just of academic interest, but that, for example, at tree level, and then, as we'll discuss later, at all loops, BCFW is naturally given in terms of on-shell diagrams. And in fact, these on-shell diagrams individually end up being Yangian invariant. Okay, so this amazing conformal and dual conformal symmetry of the theory, this remarkable fact that the theory is conformally and dual conformally invariant, totally unobvious in the Lagrangian, is actually a feature of every on-shell diagram individually. Every on-shell diagram individually sees all these symmetries. And that's a fact that is really obvious, only becomes obvious when you go all the way and connect it to the Grassmannian with that formula, with the integral, with cyclic minors and all that stuff, as we showed, right? The passage from GKN to GK minus 2n, the magic of the cyclic minors was very important for that. Okay, but sort of physically, it's remarkable that when you just glue together the on-shell processes, it makes manifest this very hidden symmetry of the theory. And of course, what's the point? Every on-shell diagram by itself is not local. Every on-shell diagram by itself does not correspond to a local space-time process. You can see it because it has spurious poles. It doesn't factorize properly. Every individual piece is not an amplitude. It's not local. It's not unitary. But it knows about all the symmetries. And so then the sort of magic is that there's some way of gluing these pieces together in order to get something which is local and unitary, and something that the pieces by themselves don't seem to care about. Okay? Now that's the physical idea. The mathematical idea, in the end, I mean, there's many aspects to it, but it's remarkable that it all flows from this generalization of a simplex into the Grassmannian to give us this positive Grassmannian. The analog of a simplex in the Grassmannian is this space of k by n matrices with all the minors positive. And it's just amazing that that's the only words you say, right? And then you just explore what the boundary structure of this space looks like. And it's much, much more intricate than a simplex. And the boundary structure of this space is associated with graphs of this form, reduced graphs of this form, invariantly labeled by permutations. And exactly the things that are built up by on-shell diagrams, which build these subspaces in the Grassmannian associated with the face variables of the graph or the bridge variables, depending on how you built them, are exactly parametrizing all the strata, all the lower dimensional boundaries of the positive Grassmannian. So it is quite remarkable that, I mean, you start from this totally algebraic looking thing, and then there's a reason why. In order to manifest that the minors are positive, you have to build them out of simple pieces, simple G13s and G23s with positive coordinates and with some rules that glue them together into these more complicated pictures that preserve positivity. Okay, and so that's where we've gotten so far. I'll just make another quick comment. These objects associated with the Grassmannian integral you can think of as, so this these on-shell diagrams you can think of as generating all Yangian invariants. Remember, the Yangian symmetry is what you get for the physical case for SL 4/4. But we can do it more generally as well. I'll just stick with this case for now. So remember, these are things that are both conformal and dual conformal invariant. And I just want to tell you, I'm not going to explain this, but just some facts. It turns out that if you just care about superconformal invariants, the super part is really important here. If you want to build conformal invariants, there are a dime a dozen. You build cross ratios, are conformally invariant. You might super naively think, pardon the bad pun, you might super naively think that you could supersymmetrize anything. You give me some cross ratio, all I have to do is add some fermions to it, and I make it supersymmetric. Not true. Okay? It's almost impossible to supersymmetrize bosonic conformal invariants. And in fact, the claim is that any conformal invariant at all is some integral over a Grassmannian with some contour and some measure. So some measure that's not specified. It can be any measure of C, delta 4k slash 4k C dot Z. So that's an interesting claim just by itself, that any conformal invariant, superconformal invariant, must be written in terms of these objects that are sort of trivially superconformal invariant, right? Remember, this thing is trivially superconformal invariant. If you do a 4x4 super linear transformation on this guy, the delta function is clearly invariant. The claim is that's essentially the only invariant you can build, and you can take linear combinations of them. And every superconformal invariant, this is the on-shell superconformal symmetry we're talking about. Remember, this is a superconformal symmetry that acts on the on-shell particles. Every on-shell chiral superconformal invariant must be an integral over the Grassmannian. That's the first claim. Then the second claim is for it to be also dual superconformal invariant. Then the measure is fixed. And the measure is the measure we've been talking about with the cyclic minors downstairs. Okay, but this is just to sort of grade what's going on already, just at a representation theoretic level. Just superconformal invariants are generated by Grassmannian integrals, and objects that happen to have both superconformal and dual superconformal symmetry are generated by the Grassmannian integral that we're talking about. Professor Strominger.
Yeah. This looks like just one function of the.
Yes. Sorry. Yes. Thank you. Thank you very much. Here you have any choice of contour you like, any closed contour you like. Okay. And in fact, I was just yeah. I'm sorry. So I was just about to say this that in this whole story, we can make any compact contour we like. The structure of the argument, I mean, the nicest way of saying what the argument is I haven't defined the Yangian algebra. We're not going to need it. But the action of the Yangian generator really turns into, it goes through all these cyclic minors. It's very important they're cyclic minors. You're hit it on external data. So it's something that hits on external data. And precisely because of the cool structure of the cyclic minors, you can pull it out of the external data and turn it into a total derivative on the Grassmannian. And then if you integrate on any closed contour, at least formally, you get something which is Yangian invariant. Okay, so, and indeed, from the perspective of this integral, all the different on-shell diagrams are simply taking different contours. Taking different contours to take residues, to set all the positive coordinates that we have to set to 0 to go to some cell, and then on that cell we have what we're left with. Okay? Okay. We can do this in twistor space, so we can do this with lambdas and lambda tildes. We can do this in momentum twistor space. The cells that we need to get sort of functions, as we discussed, so in the end, we're going to get an integral of a form for k hat and n associated with some cell, delta of c and lambda. And the whole point is that we choose the dimensionality of this cell. So any on-shell diagram associated with some cell is given by this guy. This form, remember, is the product of all the d log of the zi for I equals 1 up to the dimensionality of the cell. We can think of this as a residue of this top form that we talked about with the cyclic minors. Okay, just taking a bunch of all the variables and setting them to 0. You can parameterize with positive coordinates any way you like, and you'll get the same form. Okay, up to sign, you'll get the same form. If we want to get a number out of this, we want, if we're doing this with lambdas and lambda tildes, remember there are a total of 2n minus 4 delta functions here. And so the dimensionality of the cell should be 2n minus 4 dimensional. Okay, so we have to choose some 2n minus 4 dimensional cell to get an actual function we have to choose gamma to be dim gamma equals 2n minus 4. If dim gamma is bigger than 2n minus 4, we solve a form. We still can integrate. If dim gamma is less than 2n minus 4, we've put some delta function constraints on the external data. And so we're living on factorization channels and lower things like that. Okay, so all the dimensions matter and have some interpretation. The things that are actually numbers that depend on lambda and lambda tilde are these dimensions. And this is also equal to the delta function for momentum conservation. I'm just sort of summarizing everything we've talked about before, so we have it all in one spot, over the Park-Taylor factor, multiplied by another exactly the same form, but with k instead of k hat. And I have some, let me call this cell gamma hat. Okay, so this is k and gamma. And now this is a delta of c and a delta of c and the momentum twistor z. And this cell, the dimensionality of gamma should now be 4k, because now there are 4k. Remember, this thing is just delta 4k slash 4k c dot z, if I wrote it out in this case. Okay, so there are just 4k constraints that are put on the cells. In this case, the dimensionality of the cells is 4k. Oh, k is k hat minus 2. And we even talked about how to relate the permutation for this cell, the permutation to this one, and the new permutation is just the old permutation, essentially dropping everything by 2 and cycling everyone over by 1. Okay. So there's a complete correspondence with you take on-shell diagrams, some cell in the Grassmannian, you drop the permutation by 2, you go to momentum twistor space, you see conformal and dual conformal symmetry, and these are building blocks out of which we know how to build the amplitude. Okay? And the building blocks manifest all the symmetries of the theory. No Lagrangian, no space-time, no Hilbert space in sight, but we somehow have things that don't care, and it's a good thing that these objects aren't local, because they don't care about one space-time, they don't care about the other space-time, they don't care about locality, they don't care about factorization, unitarity. They're just manifesting all the symmetries of the theory. All right, so what's the big question then? The big question is, what tells me that I want to add up particular sets of on-shell diagrams to get the amplitude? Okay? Now you can say BCFW recursions tell me to do that. All right? And so in other words, I told you how to build these on-shell diagrams by BCFW recursion. We derived BCFW recursion, although there was a little sleight of hand at some point where I told you these poles vanish at infinity. Why do they vanish at infinity? Because of secretly there's this dual conformal invariance. Can you prove they vanish at infinity? Yes, but by a kind of a out-of-the-way, detoury argument. Okay? Okay, so there's some magic in that. But nonetheless, there's a completely concrete rule for how to build on-shell diagrams corresponding to doing BCFW recursion. So if I take that set of diagrams, I'm guaranteed to get the answer. Okay, so I like to think about BCFW recursion as kind of a halfway meeting point between sort of two worlds. One world of sort of standard local quantum field theory, where you do some responsible things and you think about poles and factorization. A little bit of magic happens with the poles at infinity and you get this representation of the answer. And then the pieces in the representation clearly have a life of their own. They satisfy identities. They come, you eventually realize all these things have to do with the fact that these pieces come from the Grassmannian. And so it's a little bit weird to say these pieces clearly have a life of their own. They clearly have a purpose of their own. Why am I putting them together in this particular way? Because I go all the way back to local quantum field theory to say, thank you very much. I should put them together in this kind of weird-looking particular way. And of course, there's not a unique way of doing it. There are zillions of ways of putting them together to build the answer. So that's now the question that we're going to ask. What kind of question is going to have an answer that's going to tell us that we have to glue together these terms in some particular way. Add them in some particular way. Okay, and that's the story of the amplituhedron now. So, in order to motivate it, let's go back. So we've already foreshadowed at some length what the amplituhedron is going to be about. We've already seen how it works for the particular case of polygons and cyclic polytopes. Okay, but let me go back and phrase something that we've seen before, just in the case of polygons, just to give some motivation for what it is that we're trying to do. So once again, let's say I want to describe the inside of the polygon. And one way that we describe this, we speak projectively always. So I have some point here, yi, and I say that y is a positive combination of the external data. Right? So we say the c's have got to be positive. And in order for the polygon to be convex, to look like this, that also implies a positivity condition on the z's. Right? So we're also going to say that the z's have to be positive too. So we think of z's as external data. They're fixed. And so this external data, lives in the positive Grassmannian G plus 3n. That's what it means. All these minors are positive. The c's are variable. We're varying over all the c's, keeping them positive. And the c's live in the positive Grassmannian G plus 1n. Kind of trivial Grassmannian here, just G plus 1n. Okay, so you see, even the notion of a polygon, as we talked about before, is slightly sophisticated jamming together of two positivities. The external data is positive and fixed, and the weights that we're using to sum over them are also positive. Okay, but let's now think in this language. Of course, this space is two-dimensional. This space is two-dimensional. G plus 1n is n minus 1 dimensional. So it's a very high dimensional space. So this is a very far from unique map. Okay, so this just says, look at every possible way of writing y as a combination of c's in this way, but it's very highly redundant. It doesn't even mean, it could well be that a particular y inside can be written in a way that has some of them positive, some of them negative. That's guaranteed to be the case. That doesn't mean that it's bad. There's just to be some way of writing it as a sum of everyone with positive coefficients. Okay? All right. Nonetheless, you might think, well, that's a little annoying that it's redundant. So why don't I go down to some cells of G plus 1n that have the same dimensionality as the space? Now, what are those cells? The cells of G1n are two-dimensional, this is just the 1 by n matrix. So just putting all but 3 entries to 0. It's 3 because it's modulo GL1 for everything. So that takes it down to being two-dimensional. So what are the two-dimensional cells of G plus 1n? The 2D cells of G plus 1n are just anything labeled by 3 places where the entries are non-zero, and then everywhere else there is a 0. Okay, is that clear? Okay, but now let's ask the question, what does the image of one of these cells look like under this C dot Z map? If I take one of these cells, what is the image of that cell under this C dot Z map? What do you think it is? Exactly. It's a triangle between points A, B, C. So here is some A here, some B here, some C there. The image of this cell, right, is just the inside of that triangle. Is that clear to everyone? Okay. Okay. So this is a little better, right? Every cell maps into some region of the some region of this inside this polygon. And so you can equally well say, look at the image of all the two-dimensional, just throw out the collection of all the two-dimensional cells. Stack of all of them, they will all cover the space too, right? That's certainly true. So you give me all the two-dimensional cells, all the triangles, just plunk them all down, and they will all cover the space. But then there's obviously something nicer you can try to do, right? So someone can say, look, but now pretend that you don't know this picture at all. Okay, so now pretend you don't know anything about this picture at all. Someone says, I have the positive Grassmannian G1n. Here are a lot of two-dimensional cells. I care about two-dimensional cells. Great. Bunch of two-dimensional cells. But for some reason, I really like this combination of cells, the sum of 1, I plus 1. These ones are great. I like that combination, right, where these label the A, B, and the C. OK? Someone else says, no, I like another one, 2i plus 1. Okay? They don't look the same. Of course, they're not the same as cells, right? These are just various combinations of cells that these people like. And if you didn't know anything about this, it would be kind of mysterious. Why do they like these funny combinations of cells? But of course, what's special about this funny combination of cells and many other ones is that this combination of cells tiles the polygon. It triangulates the polygon. Okay? So there's a clue. If someone says, I have some random seeming collection of cells where there's something good about it, in this case, what's good about it is not seen in the Grassmannian G1n. You don't see it in here. These are all like various random looking cells. Okay? What's good about it is seen under this map, where all those cells get mapped into a space of the same dimensionality. They all live in the same place. They're all top dimensional in this space. They're all boundaries in this space. They're all various distinct boundaries inside G1n. There are different sides of the simplex in G1n. But under this map, they all get mapped into top dimensional regions in Y space. And together, they cover and triangulate the region that we defined in this way. OK? So that's a clue for what is going on. And of course, as we discussed before, every one of these terms, when I go and compute a canonical form, we're not going to talk about the canonical form. We're just going to talk about the geometry today. But when I go and compute the canonical form associated with every one of these pieces, they have singularities on these spurious internal boundaries that cancel in the sum, and they only have the singularities associated with the outside. So there are many different representations. So that was a very early clue that the singularities, the spurious poles in BCFW, canceled in a way that was very reminiscent of triangulation. Okay? And so that's exactly the thing that is going to be now generalized. OK. But we've also seen that the building blocks, so the sort of analog is these were two-dimensional cells of G1n. Okay, and they're the building blocks that out of which we could triangulate this polygon. More generally, we've seen these, for example, in momentum twistor space, we've seen these 4K dimensional cells of GKN. Remember, we're supposed to think about the positive Grassmannian as the Grassmannian analog of simplex. So it's really a close analogy, right? You know, it's just that the simplices, there are lots of different shapes of them because the Grassmannian is curvy and the boundary structure is much richer. Okay, so there's not just one shape simplex. There's zillions of different shape simplices. But we've talked about the building blocks. We've talked about simplices. And now we have to see some space in which these simplices are gluing together to build an object that doesn't much care about how you triangulate it. It doesn't even care about describing it in that particular way. Okay. Well, that's just to say that we have to find some kind of Grassmannian cousin of a polygon or a polytope. And so that's just what we're going to do. OK, so here's the definition. Instead of talking about just y, which is a point in projective space, we're going to talk about something that's itself a k-plane. Okay? So y is going to live in the space of k-planes in k plus m dimensions. And m will end up being 4 for most of our physical applications, but we'll be interested in lower m and maybe even higher m as well. Okay, so this just means that alpha runs from 1 to k, and I runs from 1 to k plus m. And I want the analog of this formula. So I want to say that y is a positive linear combination of positive external data. Okay, so here the z's are going to be thought of, at least for now, as fixed external data. In k plus m dimensions. Where all these minors are positive. So it's in the positive, it's in its own g plus k plus mn. But now we're going to vary over the c's. Okay, we're going to vary over the c's. And since here, whatever I do with y is only defined up to k by k linear transformations on this index, because I'm just talking about k-planes, whatever I have to do with the c has got to be defined up to k by k linear transformations. So c has got to live in a Grassmannian. And what notion of positivity am I going to generalize from here? I'm going to ask that these c's vary over the entire positive Grassmannian G plus Kn. Okay? So this thing is, this is a subspace. So, you know, here is G, K, K plus M. And this is some kind of part that lives inside GK, K plus M. You give me fixed external data. This is just some top dimensional part that lives inside GK, K plus M. And that's this tree amplituhedron, A labeled by N, K, and M. Now we're going to spend some time understanding this space, understanding the geometry, learning to triangulate it, thinking about it in various ways. But let me just say some general things for now, and also keep going and define things to all loop order while we're at it. So, so actually, after we see what the notion of loops is from this more mathematical point of view, it'll be easier to see how to think about the all loop recursion relations when we come to them next week. That's why I decided to invert the order of a presentation. Okay. Let me make a few comments about. So, any questions about this definition? Is it clear where this thing lives? Okay, so it lives in the space of k-planes in k plus m dimensions, and it's a part of it. Okay, so it's some. It's the analog of a polytope, but it lives in the space of k-planes in k plus m dimensions. Some comments. First of all, this thing has a nice cyclic property. When m is even, we can talk about it for any m, but when m is even, A of n, k, and m is actually cyclically invariant, dead invariant. You remember we had this annoying twisted cyclic symmetry? Where we could take Z1 to Z2, blah, blah, but Zn had to go to -1 to the k minus 1, Z1. But in our definition, we do exactly the same thing with the C. So C1 goes to C2, blah, blah, Cn. So this k is now k plus m minus 1. This is -1 to the k minus 1. And so in C dot z, when m is even, there's no sign. Okay, so the space is just beautifully cyclically invariant when m is even. Okay, so that's one comment. All right, so another one are various things that it generalizes. So let's say that we stick with m equals 2 and k equals 1. So what is m equals 2 and k equals 1? Well, that's just y, just a single y, because k equals 1. yi is equal to, and k equals 1 is c1 z1i plus dot dot cn zni, where I runs from 1 to 3. Well, that's just our friend, the polygon. Okay, so m equals 2, k equals 1 is the polygon that we just talked about. In fact, any m and k equals 1, it's exactly the same story. But now the z's have to be positive. And if you remember, the polytope that we get out of the convex hull of a bunch of points where the minors are all positive, it was the definition of the cyclic polytope. Okay? So when for k equals 1 and any m, we get a polytope, and it's a cyclic polytope. You can actually relax the restriction that the z's are all positive. In fact, we're just going to come to this in a moment, but what we really need is for this map to be well defined. We even talked about this way back here, right? Way back here, we said that if you write down a formula like this, it's not guaranteed that it makes sense projectively. If the z's are random, it's possible that the right-hand side could be 0 somewhere, and that's incompatible with the projectivity. So the z's have to have some kind of positivity in order for the sum never to be able to go to 0 on the left-hand side. In 2 dimensions, the only shape you ever get for a polytope is a polygon. In higher dimensions, you're going to get lots of shapes for polytopes. What that means is they all correspond to some choices for the vertices such that this map is well defined. Okay? So there's all kinds of sign patterns that you're allowed to have for the minors. What I called, and I promised I would never say the word again, but I'll say it one more time, the oriented matroid associated with the external data. There's all kinds of matroids associated with the external data that are compatible with polytopes. And that can be done in the Grassmannian as well. Okay, so there's some restrictions in order for the map to be well defined, but you don't have to make them all positive. Okay, so there's a whole notion of polytopes in the Grassmannian, and the amplituhedron is simply the cyclic polytope in the Grassmannian. It's a generalization of the cyclic polytope into the Grassmannian. Okay, so another simple example is when n is equal to k plus m. Okay, now when n equals k plus m, this map is also very simple because y alpha I is c alpha I z a, oops, what am I doing? C alpha a z a I. But if a runs from 1 to n equals k plus m, and I also runs from n to k plus m, then this Z matrix, just by doing a linear transformation on it, I can bring it to the identity. So in that case, Y is just the same as the image of C. And so when n is equal to k plus m, the amplituhedron is nothing other than the positive Grassmannian directly. So in this case, what we get is just the positive Grassmannian, G plus k and n equals k plus m. Okay, so you can see that the amplituhedron is a joint generalization of polytopes, cyclic polytopes, and the positive Grassmannian into the Grassmannian. You should really think of it, if the positive Grassmannian is the Grassmannian avatar of triangles and simplices, then the amplituhedron is a Grassmannian avatar of cyclic polytopes. These more general Grassmann polytopes are also interesting, but OK. All right, any questions about this? Yes?
Is the variable that turn into Grassmann polytopes?
Yes, so there are some funny things here, some of which we had talked about before. So the Z's are fixed external data. They're higher dimensional, right? There are m plus k variables. So that's more than the variables that we see in the momentum twisters. As we talked about 3 weeks ago, that's where all the super information lives. All the helicity information lives, and then there are even nicer ways of thinking about it as differential forms on the momentum twistor space. We're going to come back to all of that now that we understand things better. But for the moment, I'm just talking about geometry right now. So I'm just sort of defining what the space is. Okay. Let's make another comment. So what are the cells? So what is the dimensionality of, that was a basic thing I should have said. What's the dimensionality of this tree amplituhedron? So the dimensionality of a tree n, k, and m, well, it lives in gk, k plus m, so it's equal to m times k. Okay? And so, so the claim is that we can tile a tree n, k, and m with some collection of images of m times k dimensional cells of G plus Kn. So this is the analog of what we just said for polygons, right? The polygon was two-dimensional. We took two-dimensional cells of G1n. We mapped them under the C dot Z map. They turn into little triangles. And then there's a way of putting the triangles together so they tile, so they triangulate the polygon. Okay, so the claim, I think it's still fair to say it's officially mathematically a conjecture, but it's true. Is that you can take this space, you can take a collection of mk dimensional cells of the positive Grassmannian that under this map are going to go into some space-filling region in Y space, and they will tile. It's possible to take a collection of them to tile. If you take m equals 4, every such way that we know corresponds to BCFW. Okay. So that's the answer to the question, is that all the terms in BCFW were like secretly filling out the amplituhedron. And they're gluing together to give this sort of master object. Okay? But I think you would agree, this definition is sort of more satisfying than saying build on-shell diagrams, glue them together, put 1 and n together, and glue these things, and so on. Right? So this is a kind of a satisfying answer to the question of, at least a more satisfying answer to the question of what the thing really is. Okay? And we will talk a little later about how we can see, just from this simple definition, the emergence of locality and unitarity. That's the real point. I have to say, that's the thing that early on in this business I found most surprising. I always assumed that locality and unitarity were made obvious by Feynman diagrams, and so anything else that you do will make it sort of much, much harder to see that it's local and unitary. And it's not the case. I mean, it's more unfamiliar to see that it's local and unitary, but we're going to see very simple properties of positivity are going to guarantee that the boundaries of the amplituhedron factorize into lower amplituhedra of the same type. Okay? And we're just going to see that come out of this definition from the fact that the z's are positive and the c's are positive. So we're going to do that in our further exploration next week. We're going to see that in more detail. But for today, I just want to give you all the definitions so we have everything in one spot before we explore. Yes?
Should we think of n as n, the number of supersymmetries?
Yes. This whole subject is somehow building a natural amplitude for any m which is associated with the Yangian of SL m/m. Okay? So and so there are all kinds of, and they have physical poles. They have it's actually very interesting to think what they look like. For lower m, they have a purpose in life that we'll talk about. For m equals 4, these objects have the property that when you go on the boundary, the amplituhedron splits in 2. For m equals 6, there are some interesting things. When you go on the boundary, they split in 3. Okay, so it's not standard local space-time physics. Standard local space-time is splitting in two. But this is some non-random thing which splits in 3. In general, splits in m/2 for even m. What are these things? What kind of physical interpretation do they have? Who knows? We don't know any physical interpretation for them, but they're certainly, they're very little explored. But they give you a kind of a generalization of the usual notions of what you mean by locality and unitarity in quantum field theory at higher m. Okay? They're something that looks like locality, something that looks like unitarity, but a different sort, of a different kind of factorization in 3 or 4 or more pieces. Okay? All right. Let me just say one thing. Again, I'm just giving definitions, and I want to show that these definitions make sense. We'll be doing a lot more exploration. But the first thing I want to do is actually show you how locality comes out of this definition. Okay? So, and it's actually necessary to do this because I need to prove to you that this definition is actually well defined. I need to prove to you that y can never, not only can y never go to 0 on the left-hand side, but in fact this matrix, thought of as a k by k plus m matrix, is always full rank. Okay, so there's always, it doesn't secretly live in a k minus 1 dimensional space. Okay, so, and I'll do this again for m even. It's just the same for m odd. I just don't want to, just as one more step that I don't want to do. So let's start with m equals 2. And I want to show that this map is well defined. And I'm going to do that by simultaneously seeing where the boundaries are. So to do that, we already know in the case of the polygon that the boundaries are zi plus 1. And we went through this argument in the case of polygons and polytopes before, but let's sort of repeat it now in this context. So now I'm going to look at this bracket. Now let me be clear what I mean by this y, because I'm going to use this notation over and over again. There are ky's. So when I write this y, I really mean y1 up to yk. Okay? And this thing, because I'm contracting everything with the antisymmetric tensor, is going to be invariant under GLK transformations. Okay? So I'm not going to keep writing y1 through yk. I'm going to abbreviate it by y. Okay? M is equal to 2. So all of these things, the bracket here is contracted with the, so let me be explicit for once, k. And if I take ZA, J, ZB, L, then I'm really contracting with the IK, J, L. Okay, so I'm contracting with the antisymmetric tensor of this k plus 2 dimensional space where all these things live. All right? So let's look at this guy. So from this definition, what is that y? What is this? So y, zi plus 1, is just the sum. So when I take the stack of all these guys together, I'm just going to get all the minors of the C matrix multiplied by the corresponding minors of the Z matrix. Okay, just a sum over all A1 through AK of the C minors. Let me write them as C minors. Well, let me just write CA1 through CAK times ZA1, ZA1 through ZAK, ZI plus 1. Okay? And now, the crucial point, these are all positive. And exactly, so let's say I didn't know it was I plus 1. Let me say I put a general AB here. I want to see, could it be that YZAZB has a fixed sign? Is it possible it has a fixed sign? Okay, so this is what I get. I have an A and a B here. Since these guys are positive, but I can make them sort of any size I like, it suffices to check whether it's possible to choose an A and a B such that ZA1 through ZAK, ZA, ZB is positive no matter what. And remember, that's the argument that we talked about if you're a blind person, how you would tell what the boundaries of a polygon are if you couldn't see, but you could do algebra, right? Is that you would, it's a sad, sad world if that's true, but anyway, I'd rather see than be able to do algebra. But anyway, if we have 1, 2, A, B, just to repeat the argument, if I'm looking at this sort of minor, now in this case, any set, ZA1 through ZAK, AB, then if there's any gap between A and B, I'm dead, right? Because one of those terms will have the wrong sign. Some of the terms will have the wrong sign. So I must have no gap between A and B. If I have no gap between A and B, then no matter where everyone else is, they're either on one side or the other side of I plus 1, and I just have to do an even number of reorderings in order to put it in the form where it's manifestly positive. Okay? So, good. So that tells us that if anything, that the only things that are uniformly positive are ZA plus 1. Okay. So great. So we learn, first of all, that YZA plus 1 is greater than or equal to 0. The boundaries, at least the codimension 1 boundaries, we actually haven't really proven this yet, but prove a little more work. The codimension 1 boundaries really correspond to YZI plus 1 goes to 0. Okay? And the fact that this is positive also tells you the map is well defined, right? If Y was not a full k-dimensional plane, then this bracket would be 0. Okay, so this also tells you that that the map is well defined. Okay, so if I go to m equals 4, exactly the same argument, and but you see how it mattered that the c's were positive here for this argument. It mattered the c's were positive and that the z's were positive. If I go to m equals 4, exactly the same argument tells me that y, zi plus 1, zj plus 1 is positive, and the codimension 1 boundaries are precisely when the same thing goes to 0. And that just by itself, that is locality from positivity. Because we've seen where are the boundaries. The boundaries, now notice there's a very interesting sleight of hand here. And we've again talked about this point before. When I normally think about the poles of amplitudes, what am I doing? When I normally think of poles of amplitudes, I imagine I have my data, and I move my data around until it hits some special place, like a factorization channel or something, right? In momentum twistor space, remember, factorization, this factorization where we had particle I plus 1 going around to j, and j plus 1, this factorization channel corresponded to this picture in momentum twistor space where the line I plus 1 intersect the line jj plus 1. And so we say in momentum twistor space that this zi plus 1, zj plus 1 goes to 0. Okay? Here, in the story of the amplituhedron, we're accessing all the singularities on the boundaries, at least for now. We'll come back to doing it the other way, as again we talked about, foreshadowed before, by imagining this higher dimensional data is fixed and we're moving y around. remember, as we move y around, the four-dimensional momentum twistors that you see are what you get by projecting through y. And so the four brackets involving the momentum twistors after you project through y are exactly these brackets in the higher dimensional space. So precisely by moving y around, so y, zi plus 1, za plus 1 is going to 0, in the space after you project through y is precisely moving the z's to do that. Okay? And so we discover that the only boundaries of this space correspond in the projection precisely to factorization channels. Okay? Once again, as we stressed when we saw this in the case of cyclic polytopes, what's remarkable is that we didn't say anywhere in the definition that I plus 1, they should come together in pairs, that we should care whether the pairs intersect or not. That's literally the emergence of space-time points and the importance of null separation between space-time points as a consequence of positivity. Okay? The only data that we gave are the twistors, the kind of null rays. Where the null rays go, they don't know anything about what they have to do with each other, but the structure tells you they should be grouped up in such a way to build points in space-time, and the boundaries of the object, which are going to reflect singularities of the form, occur when the corresponding space-time points become null separated from each other. Okay, so that's really, again, locality from positivity. We're going to see unitarity from positivity soon when we see what happens on these boundaries. So when we go to these boundaries, we'll show that you actually factorize into two lower amplituhedra. Okay. All right, so, but let me just finish defining things. And now I want to talk about the loop amplituhedron. Okay. And we're going to do this by thinking about what it would mean to hide particles. So this is all just sort of loose motivation. And we're gonna do this already at the level of the positive Grassmannian. So what do I mean? Imagine you have a bunch of columns. So go back to the Grassmannian. The first thing we're going to do is generalize our notion of positivity from the positive Grassmannian to something a little bit richer. Okay, but imagine you go back to the Grassmannian, and I have I have a stack of columns. Each column corresponds to some particle in our usual picture. But let's say I just want to forget about some columns. Okay? For example, I want to forget about column 1, forget about column 7. I just want to remove and forget about some columns. In just a moment, it's going to become clear that if we want to have this idea of removing or hiding particles, they actually have to be done in consecutive pairs. We can't do them one at a time. We have to remove them two at a time. Okay, so we'll see why in a second. For now, let's just say that I'm doing it. So I want to remove two particles at a time. And the particles are going to be, let's call them A1, B1. So those are the labels of the columns. Then I have 1, 2 up to M. And then I have A2, B2, and then M plus 1 up to N. So let's say, just as an example, I started off with 4 extra particles than I wanted, and I'm just going to remove, I want to get rid of the first 2 columns and these columns. So let's think about what, I mean, it's sort of, we can say this very geometrically, but it's also very easy to do it in the following way. I can always do a GLK transformation to put A1, B1 in the form 1, 1, and 0 everywhere else, and A2, B2 to look like 1, 1, 0 everywhere else, like that. Okay, so in this way, there's clearly, there's two preferred sets of two rows in this matrix, and then the whole bottom of the matrix. And then I want to forget about A1, B1 and A2, B2. So literally throw them out. Okay, so I'm going to just throw them out, and I'm going to now get a matrix that maybe down here is K, and then here's another 2, and then here is 2. Okay, so I have a matrix which has a K by N matrix down here, C, and then it has some matrix 2 by N matrix here, D1, another 2 by N matrix, D2. Okay? And let's say that this original matrix was positive. Everything was positive to begin with. Okay, now, this new matrix, these D's and C are not random. I can say something about a lot of the signs of some minors made out of these matrices. For example, all the minors of C are positive. Okay, why are the minors of C positives? Because they're just part of the big K by 4 by K by 4 minors of the big matrix, right? With this set here and this set there, the minor involving this column, that column, and everything else. Okay? So that's how I can predict that all the signs of C are positive. Notice that that explains why I had to hide these particles in pairs. Let's say I was just hiding first an A1 and then an A2 and so on. Then I couldn't say whether they were positive or not, because they would depend on how the indices were ordered relative to the other variables, to the guys that I'm hiding. But precisely because I'm hiding them in consecutive pairs like this, once again, the ordering does not matter. Okay, and so I just learned that the minors of C are positive. So what I have is, so here is a sort of a picture. So I have a K-plane C. I have all the minors of C are positive. But also, by the same argument, if I put D1 in C or D2 in C is positive. And of course, the whole thing is positive. D1, D2, and C. All of these are positive. So the act of hiding particles has produced now an interesting generalized notion of positivity. Now I have not just a K by N matrix. I have a K by N matrix. I have a K plus 4 in this case, K plus 2 times 2 matrix, where the bottom K by N minors are positive, but also taking any number of these D's also gives me something positive. And once again, notice how it matters for all of these statements that I hit things in pairs. For example, you might say, oh, does it matter if I put D1 upstairs, D2, D1, or D1, D2? No, it doesn't matter, okay, because it's an even dimensional thing. It's a two-dimensional thing, so I can permute them any way I like. Okay? Notice also that this statement only involves minors of D's together with C. Never a statement just about D by itself, or any of the D's by themselves. These D's are, in fact, only defined up to anything proportional to the C's. So the D's really live in the space. If I have a big K plus, if I have a big n-dimensional space, they live in the space where I project through C. Okay, so the picture in this case, and actually for any L, is that I have this n-dimensional space. C lives in is a K by N plane. In this n minus K dimensional projection through C, I have a stack of two planes. D1, this is these are all two planes. DL. And they have the property that we just said, that if I take any subset, d alpha 1, d gamma 1, d gamma Q, and C, then all these minors are positive. All these are positive in the sense of the positive Grassmannian. All the minors are positive. Okay, so the notion of hiding particles has given us an extended notion of positivity in the Grassmannian. Not just k-planes, but k-planes with any number of 2 planes in the complement space to C. Okay, in the space after you project through C. And all of these set of geometric objects have to have some positivity conditions that are reflected in all these minors being positive. Notice that I could do this not just with 2 planes, in fact, with any even dimensional planes that I like. Okay? But the simplest case is 2 planes. And that means that the kind of the first time I can talk about this notion is with m equals 4. Okay? So really there's no notion of this loop positivity until we get to, oh, sorry, I haven't talked about m yet. Sorry, never mind that statement. All right, so I'm going to call I'm just going to call this extended matrix, this whole extended set of C's and all the D's, I'm going to call that curly C. Okay, so it's curly C, and there's an extended positive space, G plus K N, and it's labeled also by L. Okay? And concretely, it's just this space. For example, the easiest case is where k equals 0. If k equals 0, all of the action is in the D's. There's not even any GKN left with. And the very, very simplest case is k equals 0 and n equals 4. I have k equals 0 and n equals 4. And I just have a bunch of 2x4 matrices that I can stack on top of each other. Every 2x4 matrix by itself should be positive, and all the 4x4 determinants that I can make by stacking any pair of them together should also be positive. That's it. Okay? You notice this is a rather different kind of positivity than with the positive Grassmannian, because it does not involve a notion of ordering. Right? Here it's completely permutation invariant thing between the different D's. Okay? And unlike the positive Grassmannian, this space does not have some canonical understanding mathematically. Okay, we don't know anything about its on-shell well, we know something about its on-shell diagrams, but we don't know anything about positive coordinates and cell decomposition and permutation, and all the rest of it is just virgin mathematical territory. There is no good understanding of what this space looks like, but again, we can define it, and it's going to play an important role. Okay, so, but again, this was motivated by hiding particles. It's an interesting fact that even though we motivate it by hiding particles, you can find configurations that satisfy these rules that cannot descend from an underlying positive matrix hiding particles. Okay? So that's kind of amusing that the property is motivated by hiding particles, but it's actually a little bit bigger than what you can do by literally hiding particles. Okay? Yes? Yes.
G plus Kn.
Yeah.
So it's something that fibers over G plus Kn.
That's right.
What's the fiber?
Oh, just these, literally these matrices, right? So I'm just saying, if you give me a C, and literally this, right? So so. I've just given it to you. The space is just the space of K plus 2L dimensional matrices modulo GLK action on this guy and GL2 action on each of these guys separately, as well as the translation of any of the D's proportional to anything in the C. That's the whole space. Okay, so so that's what it means that it's defined in the projection through C. And you can see that because the only statements I'm making involve minors involving C and the D's together, but the C is always sitting there. Okay? So that's it. So that's very explicitly what the space is, and we can ask what the region is that's compatible with these positivity conditions.
It's not just like an less simple description of like the part of the flag variety.
It's not, well, for one thing, we have many objects of this sort, not just one of each dimension. I mean, it's probably some, it probably is some small. as far as the actual space, it's I'm sure it's something completely standard. The part that's not standard is, I mean, it's totally standard to say that you have something and you have a lot of things that live in the projection through it and so on. Another way of saying this is it's like you take this K-plane and you mark a lot of 2 planes in it, and then after you project through it, you get a lot of 2 planes left. There are lots of ways of there are lots of ways of describing it. The novelty is the positivity. Okay? The novelty is the sort of positivity condition. Okay, so let me finish describing then the all-loop amplituhedron. And here I'll stick to m equals 4, although as you can see, we can do something like this for any m, and we can even do it with not just 2 planes. But anyway, the part that will be relevant for physics will be 2 planes. So this is now going to be labeled by n, k, m, and l. And so what is the space that it's going to live in? Well, the counterpart to that is that I'm going to have y. Remember, the data by itself, the z's by themselves are now, so now this is k-dimensional in k plus 4 dimensions. This is the 4-dimensional space projected through y. The data themselves is this, after I project, these are literally the momentum twisters, or z1 through zn. These are the actual momentum twister data. Okay? And on top of that, all of those 2 planes, the analog of those 2 planes, are going to be 2 planes in 4 dimensions. So let me call this L1. This is a 2-plane in 4 dimensions up to L, so capital L. Now remember, what are 2 planes in 4 dimensions? There are lines in P3. Those are points in spacetime. And those are the loop momentum variables when we drew our dual graphs a while ago, when we thought about, and well, I'll come back to this more explicitly later. I'll remind you how it worked more explicitly later. But our loop integrand variables were points in the dual spacetime, which are lines in momentum twister space, and are just 2 planes in 4 dimensions. Okay, so this data, the y, we have the y before. In addition to y, we have L lines in P3, L 2 planes in 4 dimensions. These are our L integration variables. Notice each one of them adds 4 to the dimensionality of the configuration, because the dimensionality of G24 is 4. So it's exactly as it should. So I'm going to call this stack of objects y. And so the all-loop amplituhedron is just y equals c dot z, exactly as before. Okay? So if I say it more explicitly, the y part is just saying that y is c alpha a za, and then each loop li L gamma I is d gamma a za. Remember, the L's are defined up to any translation by y. Okay, so I can do any that I'm modeling out by that. So the L's are defined by any translation by y, because the D's are. The D's are defined by any translation by c. So the L's are defined by any translation by y. That's why they live in the space projected through y. Okay, with the positivity, with of course all the z's positive as usual, and and the condition that we just had on the d's. So any set of the d's, d gamma 1 through d gamma q for any q, and c are all positive. Okay, so this cuts out of the space of k-planes in k plus 4 dimensions and 2 planes in 4 dimensions. So in this joint space of k-planes in k plus 4 dimensions and 2 planes in the 4 dimensions complementary to y, some region. Okay? Right? And okay, so the claim is if by hook or by crook, however you got it, you got the canonical form for this region. The claim is that it does have a canonical form. It has boundaries of all codimension. It's a positive geometry in the language that we at least loosely introduced before. So this space has boundaries of all codimension. There is a canonical form associated with it, and that canonical form is the all loop integrand for n equals 4 super Yang mills.
Does it make sense for odd n, or do you really want the even n?
Let's see. I have to think for a second. I mean, certainly these have to be even dimensional. So we could do it for 4 planes, 6 planes, anything. I have to think whether we have trouble if m is odd. I don't think we have trouble with if m is odd, so long as these things are even dimensional. Okay? All right, well, next time we're going to start by, so that's it for the definition, right? So I think, so this is just to get you oriented to the spaces that we're living in and the kind of definitions that we're talking about. So as you see, part of this story is much closer to being, I mean, is more familiar both physically and mathematically. We have a huge amount of control on what the, we know essentially everything about how to write tree amplitudes, at least using BCFW. We know all the cells. We know everything about this. And also mathematically, we know everything about the cells of the positive Grassmannian. And it's still an interesting sort of, as I mentioned, an open mathematical problem to really understand ab initio. If the physicists never existed, if we didn't know about BCFW and recursion relations and all of the rest of that, how mathematically would you triangulate this space? How would you discover that these pieces glue together, fit together, and so on? So that's already an interesting question. That question is sort of very beautifully and simply understood for m equals 2. So we'll start talking about the sort of simplest case of the amplituhedron for m equals 2, where we can see a lot of these things sort of nicely in action. And I suspect that this is solvable, a very, very solvable problem for general M. When we go to loop level, the story gets much more interesting. First of all, we know how to generate BCFW recursion in principle to any number of loops. The person sitting in the back row on his laptop knows more about the integrand for n equals 4 super Yang mills than anyone on the planet. And so if you want to know the explicit answer for at some number of loops, some number k, just ask Jake. But what's the status? We probably know the answer for MHV at 4 points, we know the answer to 10 loops from other means. Okay, but for k equals 1, k equals 2, I forget where it tops off. I mean, where does your laptop crash now? Right? It's like.
Formulas for all n and k through 3 loops.
Okay.
BCFW works, of course, much higher than that.
Yes. But just in practice, so Jake has a package that you can, another package that you can play with, not just a positories package, a BCFW package that you can play with that generates all the trees. So everything you want to know about tree amplitudes, whether you want it in momentum space, momentum switcher space, whatever, you just type in NKL, N and K, and what representation you wanted, and it'll spit it out. He does not have an analogous package at loop level. That's only on his private laptop. But yeah. Okay. Oh, good. Fine. Anyway, so but just so you know, it's kind of quite a bit wilder. One loop, no. One loop is no problem. One loop is very, very easy. 2 loops and higher is really starts being wilder. I haven't told you what the all loop BCFW is. That's what we'll do in the second lecture next week. But anyway, there is a systematic way of doing it, but much less is understood about it. It's not, for example, just to give you a feeling for it, every way of doing BCFW produces the same number of terms. This is something kind of cool. So if you want to do, and those terms have a very nice combinatorial interpretation. They're the famous Narayana numbers. Okay, so they're refinements of Catalan numbers. We'll talk about a little bit again in the couple weeks. But it's kind of cool. Every way of doing it, every way. You want to do 8-point n squared MHV, it's 20 terms. 20, 20, 20, 20, 20. That means that there's stacks of 40-term identities that say that this 20 terms equal to those 20 terms and so on. But it's an interesting, so every one of those things corresponds to a certain triangulation of the amplituhedron by those cells, right? So there's something interesting about that, right? That, oh no, sorry, not every one of them. Some triangulation of the amplituhedron we do not get from a BCFW, but yes, yes.
Just for those triangulations that come from BCFW, there's something like 12,000 of 20 terms.
Right, oh, that's right. Yeah, so there's gazillions of them. There's gazillions of them, but always 20 terms, right? So there's something very rigid and interesting about these triangulations look like. Not true at loop level. Starting at 2 loops, there's something kind of floppy about what they look like. And so, and relatedly, we don't understand what this positivity structure looks like mathematically either. Okay, so there's a lot to be understood. But let me just make one comment before I let you go. Something sort of amusing here. Let's specialize this story down to something that seems really simple. K equals 0. Okay, let's do k equals 0. So that's MHV, right? K equals 0. The y is gone. There's no y. So what do we have for k equals 0? And let's say one loop. K equals 0 in one loop. Then I just have one of these L's. And I runs from 1 to 4, right? Because k equals 0, m equals 4, right? So I runs from 1 to 4. So I have some 2 by 4 matrix is a positive linear combination of external data that's 4-dimensional. So notice an amusement, notice that k equals 0, m equals 4, L equals 1 is the same as k equals 2, m equals 2, L equals 0. It's the same as the tree amplituhedron for m equals 2, right? So that's really nice. That means that when we study the m equals 2 amplituhedron, next time we are secretly doing one loop MHV calculations. Okay, so we're going to understand the one loop MHV formula. Okay, all right, that's it.